In this video, we're going to learn about the mole and mole calculations. And that begins with Avogadro's number, not to be confused with avocado's number, but Avogadro's number, which is 6.02 times 10 to the 23rd power. Seems like a really big number, and it's unfathomably large. But it is what it is for very good reason. Now, in chemistry, we use a concept called the mole. It's a unit to measure particles. And the reason why we don't just say, there are 10 sodium atoms is because 10 sodium atoms would be impossible to measure out. Sodium atoms are impossibly small. Even molecules like glucose, C6H12O6, a lot of atoms there, but really the mass of that is impossibly small to measure out. And so we use the mole. The mole is going to be Avogadro's number of particles, whether those particles are atoms or molecules or whatever. For the purposes of this unit right now, we're just going to look at atoms. So a mole is Avogadro's number atoms. And molar mass is going to be whatever the mass is of 1 mole of a substance. So different atoms have different masses. A hydrogen atom has only 1 proton in it and maybe 1 neutron, but most isotopes or most atoms of hydrogen will be of the isotope that has only just 1 proton. On the other hand, you look at uranium, that has 92 protons, and the average uranium atom weighs 238 atomic mass units. So you can see every atom weighs its different mass, and sometimes there can be a pretty big variation in them, which is why we need this molar mass. So how do you find the molar mass of an element? Well, you look at the periodic table. And what's interesting is the periodic table, this average atomic mass is also the molar mass of the element. And so what this means is that although the average carbon atom will weigh 12.011 AMU, a mole of carbon atoms, meaning 6.02 times 10 to the 23rd of them, they will weigh 12.011 grams. So 6.02 times 10 to the 23rd power carbon atoms, they weigh, I'm just going to put a colon here, the mass of this is 12.011 grams. And actually, we're going to round all of our molar masses to the hundredths place. So I'm just going to drop off this last one here, and we'll just use the periodic table to find the atomic mass to the hundredths place. So that many carbon atoms have that mass. And also you could say that 1 mole of carbon atoms weighs also 12.01 grams, because the mole is just Avogadro's number atoms. So it's the same. That should be a 12. So we have that concept of molar mass. 1 mole weighs that many grams. So what we could say is that 1.00 moles of iron, they contain 6.02 times 10 to the 23rd atoms, and they weigh 55.8. Well, in this case, I'm going to round the 4 up because 845, that 5 rounds it up to 5 grams. Now, I could be talking about iron, I could be talking about copper, I could be talking about anything, and exactly 1.00 moles of it will contain that same number of atoms. What differs is the molar mass, right? The mass of it, because if we're talking about iron, it's heavier than, say, hydrogen. But I just wanted to point out the number of atoms in a mole is going to be the same regardless of what substance we're talking about. But okay, let's say we're talking about 2 moles of iron, or we could have anything like 1.39 moles of iron. How would we be able to mathematically figure this out? Well, what we're going to do is we're going to do something called dimensional analysis. And any dimensional analysis problem, we start out simply by writing out whatever number is given to you in the problem and the unit. So it's 2.00 moles of iron, which is Fe. And what we need to do is multiply this by a conversion factor. And every time our conversion factor needs the units of whatever you started with to be in the bottom. So this is going to be moles of Fe. And you can see that they cancel out. And on the top is whatever we're trying to find. Now, what we're trying to find is atoms. And it's specifically atoms of iron. But we're going to put atoms here because that's what we're trying to find. So always what we're trying to find in the numerator, right, over what we're coming from, which is in the denominator. And so we need a conversion factor to relate these two. Well, we know that 1 mole contains Avogadro's number atoms. So it's going to be 6.02 times 10 to the 23rd atoms. So mathematically, what we have to do here is we take the 2.00 and we multiply it by 6.02 times 10 to the 23rd power and divide by 1, which doesn't change anything. And what we get is 1.20 times 10 to the 24th atoms. And we need to have 3 sig figs here because our initial measurement was with 3 sig figs, 2.00. And also Avogadro's number is also to 3 sig figs, so that's not hindering us. Our final answer has to be to 3 sig figs. Now, if we have 2.00 moles of iron, well, they weigh how many grams? We know that the molar mass of iron is 55.85 grams per mole. So we start off with our 2.00 moles of Fe. We know that we need to divide by wherever we're coming from, which is the moles. And we need to multiply by whatever we're trying to find. Well, we're trying to find grams, so the grams go on the top. And we know from the periodic table that 55.85 grams of iron are in 1 mole of iron. And that brings us to, if I do 2.00 times 55.85 divided by 1, that gives us 111.7, but since there are 3 sig figs, we can round this to 112 grams of iron. All right. Now, we can go in reverse. A sample of beryllium contains 9.03 times 10 to the 23rd atoms. It contains how many moles of beryllium? Well, we need to start with our number that's given in the problem, 9.03 times 10 to the 23rd atoms. And we're going to multiply this by a conversion factor that has atoms in the bottom. And what are we trying to find? Well, we're trying to find moles of beryllium atoms. So I'm going to put moles here. And the moles needs to be therefore on the top. So our atoms and our atoms cancel out, and the only unit that we're left with is moles. Now we know that 1 mole contains Avogadro's number atoms. So 6.02 times 10 to the 23rd atoms. And if we put this into our calculators, we would find that 9.03 times 10 to the 23rd times 1 divided by Avogadro's number is going to equal exactly 1.50 moles. Important point, everybody. If you are dividing by Avogadro's number, you need to type it into your calculator with parentheses around it, or else you're going to get something like 10 to the 47th power it'll come out to, or something like that, or 46 rather. So you need to make sure that your denominator here is in parentheses. Otherwise, what you're telling your calculator to do is not what's written on your paper. All right, anyway, that many moles of beryllium atoms, and weighs blank grams. Well, we can take our 1.50 moles and we will multiply by the molar mass of beryllium, which, if I move myself over a little bit, come on, no, let's make you smaller and let's drag you over. There we go. Okay. So for beryllium, our molar mass is 9.01 grams over 1 mole. And I show it like this time because I want the moles to cancel out. Previously, I had the reciprocal, but now I want the moles to cancel out, so I got grams over moles. And what this brings us to is 13.5 grams of beryllium. And there we go. Next, and finally, we have a sample of carbon that weighs 6.00 grams. So we have 6.00 grams of carbon. So we can find out how many moles it contains. It contains, well, let's see. We know that we're trying to find moles and we have to get rid of grams. So our grams are going to be on the bottom. So they cancel out. And we need moles on the top. And we know that 1 mole weighs 12.01 grams. We get that from the periodic table. And so from here, we could divide them out. 6.00 times 1 over 12.01. That is going to give us 0.500 grams, moles rather, of carbon. So we have exactly half a mole to 3 sig figs of carbon. Now, if we're trying to find out the number of atoms, we can do this. We could do this by taking the mole and going to grams, but I do want to show you one thing. You see, if you start with grams, you can go to moles, and from moles, you can go to atoms. And our bridge to get there is that from grams to moles, we need to use the molar mass, which I'm just going to abbreviate as MM, and you get that from the periodic table. Getting from moles to atoms, we need to use Avogadro's number, which I'm just going to say AN, right? Avogadro's number. That's our bridge. And you can also go backwards. It's just that we're using reciprocals, right? Any conversion factor you can flip back and forth according to the direction that you're going in. But notice that you always use moles as your bridge. You can't go from atoms directly to grams or grams directly to atoms. You need moles as your intermediate, and you would need to do a 2-step calculation. But you can get from moles anywhere or from anywhere to moles in 1 step. So I'm going to show you how you could approach this second problem in 2 steps. We could say that we're starting with 6.00 grams of carbon. Now, if we're starting with grams and going to atoms, we need to first go to moles. So I could put in my 1 mole over 12.01 grams. And then from here, so I get this canceled out, but we've got 1 mole. Well, we're not trying to find moles, we're trying to find atoms. So I need to put atoms where we're going over where we came from, which is moles. And I'll cancel out the moles, and I will get atoms. Now, this last conversion factor is going to be Avogadro's number. We know that 1 mole contains 6.02 times 10 to the 23rd atoms. And notice all our units on this left side cancel out except for atoms. On the right side, there's only atoms is what we want. So we've set this up well. So what we'd have to do is we'd have to take 6.00 times 1 divided by 12.01, and then multiply that by 6.02 times 10 to the 23rd, and, well, divide by 1 again, which doesn't change anything. So basically, we take our half mole of carbon that we get from this part, and we multiply by 6.02 times 10 to the 23rd, which gives us ultimately 3.01 times 10 to the 23rd atoms. One final thing that should be noted is that these conversion factors, they all involve moles, and always when you have moles, it's going to be a 1 next to it. So just keeping that in order, it's going to always be a certain number of grams for every 1 mole. And it's always going to be Avogadro's number atoms for 1 mole. So that'll help you keep the conversion factors in order. Anyway, I hope this video has been helpful. Feel free to leave any questions or comments in the comment section below. Thanks a lot for watching.